Hi, my name is Joseph, and today I'll be presenting on my independent work, which is building a chess engine. So why build a chess engine? Well, the problem of chess is famously complex, with estimates such as Shannon's number positing that the number of total chess games that you can play might even outnumber, say, the atoms in the universe. And the goal of a chess engine is to find the next best move in any position. For example, here, this engine suggests d4, e4, and knight f3. So when we think about chess computationally, we can model it as a search tree where we could enumerate children nodes by looking at the positions we reach when we take the next legal moves. In classical chess engines, one popular approach builds upon an algorithm called minimax, specifically a truncated version where we cut it off at some search depth. And then we apply something called a static evaluation, which is just some function that white wants to maximize and black wants to minimize. For example, if you look at white's material minus black's material, if this value is high, then white has more material. If it's low, then black has more material. So we'll extend the search tree up to some specified depth, in this case 3. We'll evaluate the leaf nodes, and then we'll go back up the tree, and each player is going to try to do the best they can, knowing what the other player would want. So in this example, between -2 and 4, white prefers 4 as that's maximal. Here, white prefers 6. Now looking at these two options, black prefers 4 because that's minimal. We can do the same thing with the other subtree, but in total, we can see that white would prefer to go down the left subtree because it could guarantee a value of at least 4. Whereas if it tries to go down the right subtree, then black can force its hand to try to get a value of -5 or even worse, -8. And in total, the time complexity of this is the breadth to the power of the depth. Here, the breadth is 2 because we have 2 children nodes at each level per each node. And then the depth is just 3. But in a real game of chess, you might have a breadth of like 30 because you might have 30 legal moves on average in any position, and the depth might be, say, 80. Now, with alpha beta pruning, this is just an optimization we can do upon minimax that maintains its correctness, but improves its speed. So we can observe that we don't actually have to explore every subtree if we keep track of just a little bit more information. We can keep track of white's best option and black's best option. So here, for example, when we evaluate this tree, white prefers 3 as that's maximal, and we'll search in a depth first search fashion. So continuing down to this tree, we can evaluate this node to be 5. So white knows at this point that it can at least get a value of 5 if it reaches this point. So here, black knows then that it will never go down this tree, because why would it let white guarantee a value of 5 when it could get 3 instead, which is better for black? And in practice, this is going to achieve the same benefits as cutting the search depth in half. One famous engine that used alpha beta search and its related algorithms is Deep Blue, which is especially notable for beating former world champion Garry Kasparov in 1997. Another approach that has become more popular as of late is Monte Carlo tree search. In Monte Carlo tree search, we have 4 stages. So first, we try to select the best candidate leaf node. Then we expand out one depth. And instead of evaluating using some static evaluation function as alpha beta does, we simulate out a random game from that expanded leaf node where we play out random moves. And the intuition here is that from good positions, you should be able to win more even under randomness. Lastly, we'll update the tree through a process called backpropagation. We also have a parameter in MCTS called the exploration factor, which controls whether MCTS is inclined to explore in more breadth or with more depth. So this is known as exploration versus exploitation. One famous engine that uses MCTS is AlphaZero, and its key insight is that instead of doing these long simulations, we can use neural nets to evaluate the positions instead. The issue is that it's very computationally expensive and it requires thousands of TPUs to get right. This project will try to replicate some results from AlphaZero building upon MCTS, but instead of using AlphaZero's really computationally expensive methods with its neural nets and reinforcement learning, we'll try to compensate by using some prior knowledge in the form of evaluation functions similar to those used in alpha beta, which requires some domain knowledge about chess to construct. Whereas again, AlphaZero tries to learn this domain knowledge from nothing, hence why zero is in its name. And we can try to feed in this knowledge to MCTS ourselves. And I also built an alpha beta engine as a comparison. So I implemented all of this in Python because the Python chess library is very space efficient and it supports all the functions needed to represent a game of chess. I also use something called p-square tables, where we assign positional bonuses or penalties to different pieces depending on where they are in the board and what phase we're in. There's two p-square tables, one for the early and middle game, one for the end game. And for example, here, the king does not want to be in the center in the early stage of the game. You can see that it has all these negative penalties, whereas it gets these positive bonuses for being in the center of the board in the later stage of the game. All of this combines to form something called tapered evaluation, which just takes a sum of material and a weighted average of p-square table bonuses and penalties based on the phase, which we can estimate based on the number of pieces remaining. In my MCTS implementation, I use early playout termination. So instead of doing these full simulations, I cut off after 0 moves. This is similar to how AlphaZero will cut off after a depth of 0, and at which point it uses its neural nets to do the evaluation. But instead of doing the neural net evaluation, I use tapered eval here, and I backpropagate this evaluation. The advantage is that full simulations where you play out a full random game are often uninformative, and you often have ties anyways. And here I can control the time it runs for, its search depth, and its exploration factor. For my alpha beta implementation, I use move orderings so that alpha beta tries to search good branches first, which allows it to prune out more information. I add on something called quiescent search, which means after we reach the search cutoff of an alpha beta, we continue searching just the capture moves. This is cheap to do because there's only so many capture moves in any position, so our breadth is not very large. And it also has the advantage of preventing tactical blunders. For example, you might end your search at queen takes pawn, and you miss that the next move after that would have been pawn takes back your queen. I used the tapered eval from before, and in my implementation, I can adjust the alpha beta search depth as well as the quiescent search max search depth. So the way I tested this is using something called ELO, which is just a rating in which players with higher ELO are generally estimated to have higher winning odds versus players with lower ELOs. I compare this, my engine, against Stockfish, which is currently the top chess engine, therefore the gold standard, with adjusted ELO. You can adjust Stockfish's ELO by introducing a little bit of error to lower its ELO. And if we can beat or tie Stockfish at X ELO in a small competition, we increase X and then we retry this until we can no longer beat it. So this gives an estimate of about 2,000 ELO for alpha beta, which would beat approximately 95% of rated human players. So you can see as you allow alpha beta to be able to see farther and farther into the future, its ELO increases drastically. And here is an example game. It plays against my friend. The engine is black, my friend is white, and my friend is rated about 2,000. So we can see that the engine plays this Alekine's defense line where it jumps around its knight for a bit. We have some early exchanges as my friend tries to take the engine just into a cleaner, more simpler endgame. And then we can see the engine starts pushing its pawns into enemy territory. Now, white tries to expand as well, try to take some space and try to infiltrate. We can see that white has infiltrated. Now we exchange one pair of rooks. And at this point, black starts to infiltrate. So you can see that black has gotten in with its rooks, or its rook. And here, a key moment, black can try to promote, and this pawn is tactically defended by a discover check, at which point white loses his rook, and my friend now just resigns, having lost his rook. Monte Carlo did not fare as well, scoring at less than 500 ELO. I won't show a video for this one, but in short, it blunders significantly more frequently. It misses these key sharp tactics, and this causes the poor performance. For future work, I'm still working on integrating some more sophisticated evaluation methods to account for more features. There are still other optimizations, of course, that can be done as well. But in conclusion, alpha beta does have a lot of advantages over MCTS. The key difference is that it doesn't get like this type of tunnel vision, and it doesn't miss these key tactical lines the same way that MCTS does. So this is my presentation. Thank you for listening to my talk. And of course, I have to give a shout out to Professor Kincaid for all the guidance throughout the semester. I really enjoyed my independent work, and I learned quite a lot. Thank you again.